We have with us too Shalini Devendrababu. Hello,
Hello.
Shalini. Welcome.
Hi. Hello. Yes. Am I
Shalini,
audible?
yes, we can hear you.
Yeah. Perfect.
Shalini Devendrababu holds a master in quantum technology from CSIC UIMP in Spain. She is currently the lead quantum eye researcher at Fractal Quantum Eye Lab. She authored a best-selling and highly rated Udemy course on Qiskit to 2,300 students, and also published Quantum Computing for Everyone, an introduction for more to 10,000 students. Course in Coursera. Her research in quantum material science and education have been published by EPJ Quantum Technology, Springer, and IEEE. She also authored three technical books on quantum computing, among which two are world first book, exclusively dedicated to product managers in the field of quantum computing, and it's been featured in European Commission Selects Books category and another book in Qiskit Metal. The title of his ponens, Mapping Quantum Industry Demands to Education, a critical analysis of skills, qualification, and modalities. Quantum technologies and computing are emerging area which offers a new paradigm to solve complex problems. Using the principles of quantum mechanics, where classical computing face limits. Due the advantage of quantum computing, today there are several industries focusing on different aspects of quantum technologies based on their physics to explore the most efficient and useful platform for implementing applications. Since the scope of the quantum companies is diverse, it is important to understand the education, skills, and qualifications required for different jobs roles. As this, we aid global education institutions in constructing concrete disciplines in this file. I will be addressing most of the dominions of quantum critical industry skills, qualifications required, and demystify the requirements of PhD. Welcome again, Shalini, and let's proceed.
Thank you so much for your wonderful introduction. And let's get started. Is my
Yes, we
screen
can see your presentation.
okay? Thank you. Okay. So let me. Okay. um, okay, perfect. So the person has already given a very warm introduction about me, and I think we can get started. So I will just give a small introduction about myself, just a very quick introduction.
Ex-
I'm Shalini. I am a
Excuse
lead
me,
quantum.
Shalini. Sorry,
Yes.
we have a problem with your microphone. It have some noise.
Okay. Am I audible now? Is it perfect?
It's perfect.
Okay. Thank you so much. I'm a lead quantum AI researcher in fractal analytics from India, and I've done my master's in quantum technologies from Spain. And I published three technical books and two a world's first book. And those books are adapted in some famous universities like University College of London and Max Planck University, DigiPen University in USA, and Carl Institute of Technology and other famous libraries in USA also. And I've published some papers in journal like EPJ Quantum Technology and IEEE Springer. So also I have two courses, one in Udemy and another one in Coursera. Those are two professional courses in quantum computing only. And I'm a coordinator in Q World since 2023. And I'm also a mentor in Q Intern. And I've been featured in Times Square, New York, twice this year, and I spoke in different universities and gave a lot of career guidance to people in top mid. So that's kind of a consulting, small consulting. And yeah, I will cover a few world to initiate the human initiatives. So this is my small introduction. So these are my three books, which has been global already. And today my talk is about mapping quantum industry demands to education, which is where we do a critical analysis of the required skills, qualifications, modalities required. So before starting, I would always wanted to make sure, wanted to give a small introduction. Why should we need to give this talk? So there are two reports which suggest, which supports my claim, where MIT Quantum Index has mentioned that there is a lot of job posts related to quantum, but there is a very less amount of industry, talent which is being present, which the industry requires at present. So the QED consortium, those report also mentioned that there is some lack of hands-on training and mentorship and clear career pathways are not present. Even when I am giving consulting to people in top mid, I realize that many people are unaware like how to start in quantum and which domain they need to take it forward. So I will try to give the best possible solution as possible. And today I'm going to share you the most important domains in quantum and what are the required skills which industry actually requires, and where you can shorten the academic and the industry gaps. So that's my active area of interest to educate people, because quantum is a novice device and it's a very niche domain. And there is a lot of research and there is a lot of money going into different startups. So the industry requires people with those skills. So if you don't have those skills, and you might not be able to get a suitable job, which I really don't recommend anyone. So this talk is about what kind of skills you can develop during a master's program or bachelor's program or during your PhD program. I will pretty much cover most of the domains. Some domains may not be missing. So that can be covered maybe in different session in different time. Okay. So I think I have given a strong introduction why I'm doing this talk and why this concept is very important. Now coming to the important point, what are the important quantum domains at present? So we all know there are different domains. For example, if you take there is a hardware platform where you have silicon superconducting qubits, semiconductor qubits, NV center, topological qubits, photonic qubits, neutral atoms, and ion trap. So every other hardware platform is a separate domain in itself, and a lot of companies, nearly 4 or 5 companies are working in a separate domain itself. For example, superconducting for example, IBM is working on superconducting qubits. Photonic qubits are done by, most of the companies like um, Quantinuum is working in photonic qubits, neutral atom, QERA is working in neutral atom, and then topological qubit. Microsoft is working on topological qubit. So, what are these skills do they require from people who wants to make a career out of quantum? So, I'll be discussing about every quantum hardware domain, what kind of skills you wanted to develop or to make your studies industry ready. And yeah, we will also be discussing about the quantum error correction, because we need to develop a fault tolerant quantum computer. If you want to develop a fault tolerant quantum computer, you need to apply the error correction codes to make the fault tolerant quantum computer to use it in the real world application. So I'll also be discussing about quantum error correction. And yeah, I will also touch upon quantum sensors. I'm not covering quantum cryptography, QML, and finance because there is not much time left. So I'll be covering those important domains which I feel as more impact and requires which has a lot of jobs in the market. So I'm discussing those domains at present. So let's start with the quantum hardware. So quantum hardware, like just now in the previous slide we have seen, there are three type of there are six type of quantum architectures. So I will classify them into three different sections. For example, superconducting qubits, nitrogen vacancy central diamond, those come under the condensed matter physics domain. Semiconductor qubits and solid state physics, semiconductor qubits mostly come under the solid state physics, though it is also a comes under the part of condensed matter physics. But semiconductor qubits means you need to use a lot of silicon, so that comes under solid state physics actually. And then trapped ions, neutral atoms, and photonics comes under atomic, molecular, and optical physics. And you might ask, what are these kind of physics I'm talking about? These are different sections of physics. For example, you have high energy physics, also you have particle physics. So under that you have different sections. For example, in high energy physics, you have reservoir computing. Those kind of concepts are also present. Okay, so that's not that hardware. We are not doing it in the quantum computing, but at present there are six hardware types, and those hardware types can be condensed under these three major physics domains. So that's what I've written here. So if anyone wants to make a career out of superconducting qubits, you should be very good in condensed matter physics. And if someone wants to make a career out of neutral atoms, they should be very good in atomic physics, atomic aim of physics actually. So yeah, let's go into every domains. I mean, every qubit structures. For example, if you can see in this particular diagram, I have mentioned about what are the key required skill sets for superconducting qubits. You can ask me how did I come up with this diagram. I have all these images in my paper, and that paper is in EPJ Quantum Technology Journal. So you can just type the title of this talk. You will get my paper, so all the diagrams are there. And how did I find out all these skills? You can find out in briefly in my paper. I mean, I have written everything comprehensively there. You can go and have a look. It should be definitely helpful for beginners and even people who wants to shift the career from one domain to another domain also. Okay, so if you see this skill set, you can see there is a lot of important skill sets like you need to develop Python programming, you need to develop the clean room fabrication. So I will condense into three different subject sections, and I will say you step by step what are the skills you need. For example, if you see one of the foundational knowledge which you require, so I've given 1, 2, and 3 points, which means that it's a step. First you should cover the foundational step, second you need to go to the experimental skills, and third you need to go to the system software and integration skills. So for the most important foundational knowledge is condensed matter physics, as I mentioned. Since superconducting qubits comes under condensed matter physics, and you need to know about the Josephson junctions, because you need to create a Josephson junctions for superconducting qubits, and you need to know about the microwave engineering, because you have to give the readout, you have to control and do the readout for the qubits. For that, you need to know about the microwave engineering. At least the foundations are very important. And cryogenic principles. Why cryogenic principles? Because in superconducting qubits, you will be uh, using the dilution refrigerator, and for that, you need to know about the cryogenic principles, because you are going to isolate the qubit at a very low temperature. For that, the cryogenic principles are extremely important. And if you try to isolate the qubits, you have a lot of problems like noise. So you need to also know how noise occurs. So those are the foundational knowledge you should definitely have. And experimental skills. So experimental skills comes if it is a hardware. If I say hardware, you should always think about the clean room for sure, because nanofabrication comes the first part here. And so the major important point in an experimental skill is nanofabrication. What is nanofabrication? You have something called clean room, where you will be having your own suit, clean room suit. You have to wear the clean room suit, and then you have to go and manufacture a chip. You have to create a superconducting chip or semiconductor chip. When I was doing my master thesis, I went into clean rooms and I was working on some semiconductor spin qubits. Although it was not, it was a short amount of time, but I had a very good exposure of what actually is clean room. So nanofabrication is very important. It's one part of your PhD program if you're trying to do your PhD in superconducting qubits. Yeah, so nanofabrication is very important skill. And cryogenics, as I mentioned, we will be using dilution refrigerator, and for that we need to know about the cryogenic principles. So one such skills are cryogenics, and then microwave engineering. Yeah, so why do we need microwave engineering? Because you need to do qubit control, and you have to read out the qubit once you measure it. For that, you need to know the microwave engineering. And measurement and automation. For example, you need to know how to, after measuring the qubit, you should know how to do data analysis. For that, you need to know Python and LabVIEW. LabVIEW is a software you might have used it before. So, and yeah, data collection and analysis. So these are very important points. Every domain, I mean, every industry expects these important small details. And how can you achieve these kind of skills? That will be I will be discussing about in the upcoming slides. Next point is characterization. So in characterization, you'll be doing scanning electron microscopy, and then atomic force microscopy is also there, profilometry, thin film diagnostics. So you'll be doing characterization. Characterization means, for example, you are creating a qubit in a clean room, and you need to know whether that chip actually works or not. The chip which you fabricated in the clean room, you should test whether that chip really works or not. So how do you check? By checking whether the chip is working under electrical. You will be testing the different properties. For example, thermal property, electrical property. Those you will check whether that chip is really working or not, and that's called as characterization. And yeah, so those are the experimental skills one requires. And next is system software integration skill that comes into the fifth software part of the domain, which also is important. FPGA based qubit control systems, data analysis is there. Data analysis, we already know we need to take the measurement of a qubit, and then you need to analyze whether, I mean, what is the output of the qubit, whether we can able to really whether the chip is actually working really well or not. So for that, you need to know the data analysis, and you need to do documentation, and then analytical numerical modeling, COMSOL, SONET, HFSS, HFSS, and so COMSOL. I think these are electromagnetic software where you'll be working. Um, yeah. So those are the important key skills which I observe when industry is trying to hire an expert. And okay, so the major question which many people ask me when they take consultation from me is whether you need to really do PhD for superconducting. If you want to be an expert in superconducting qubit, do they really require a PhD or not? And this is the major important question which comes to me all the time. And I would say definitely one should have a PhD because many people say you can only have masters, but you can have masters degree qualification for QML and other kind of stuff. But when it comes to hardware, you need to have a PhD because if you see all the skills mentioned requires a lab setup to work. So until and unless you work in lab for a couple of years and become really good at it, you can't work in an industry where the major important point of an industry is to sell the product. So if you want to sell the product, you should know how to create the product. How so if you want to know how to create the product, you should work in the labs which teaches you, which makes you skilled. So I would definitely suggest people to go to PhD because this is a niche skills and it requires a lot of training to become an expert. Okay, so for most of the quantum hardware, I can safely say all the qubit hardware architectures requires a PhD, 100%, because it has a lot of niche and all uh, you know um, those important subtle things are can be understood only when you do training in labs. So PhD is extremely important. Though there is masters and bachelors and equivalent industry experience, nothing can beat PhD actually. Next is qualifications. So whether what kind of qualifications do you need? Um, you need to know about physics because physics is a major part of this hardware. Not only superconducting qubits, but also among all the hardware architectures, physics is very important. So you can have a physics degree. Maybe you can have an experimental physics degree, or you can be an engineering. You can have engineering degree also because you're going to make a product. So engineering means creating a product out of math and physics. So you can have engineering field, I mean degree also, um, physics also, electrical engineering. Those are any kind of engineering degree like electrical engineering and electronics engineering can of course work. But if you do a PhD, it will If you do a PhD in hardware, it will most probably will be PhD in experimental physics. So yeah, I think the superconducting hardware is done. Next, coming to semiconductor spin qubits, I can safely say whatever skills I mentioned in the superconducting domain is the same for semiconductor also. Most of the thing it is same only. Yeah, so I think we have already discussed about what are the key skills required for the superconducting qubit. So I will not discuss it further. And what are the qualifications? Again, you need to do have a PhD in electrical engineering or physics degree or quantum optics or applied physics. Those are the name of the qualifications people actually term about. So it doesn't really matter. But if you have a PhD in physics or PhD in engineering or PhD in math or PhD in computer science, I have observed those kind of trends in the career pages of different companies. So these degrees, like the name doesn't matter, but you need to have the relevant skills. So that matters a lot. You can't just apply for error correction role by having uh, cryptography experience, right? Cryptography is different and error correction is different, and you need to have a relevant experience, not exactly the name. So you don't have to worry about okay, I have PhD in mathematics. Will I be eligible? If you are having a theoretical experience to the particular domain, then it's fine. Otherwise, I that's not an issue. Again, coming to the degrees, though the graph shows masters. When I was observing and doing this graph, I was so shocked why masters is required. Then I again checked multiple career pages. Um One of my colleague when I was doing masters was a master student himself, but also he is working in clean room labs. So upon asking to the person, he mentioned that he has a good amount of experience in working in clean rooms. So he kind of got hired to do some kind of industry related works. So I think masters plus 2 3 years of relevant experience may help, but mostly if you want to go in industry, they require a PhD and a master's plus couple of years of experience. You know, it again this depends on what kind of where you are working in. So since I worked in Spain, in particular lab called IMBCN, I'm in Barcelona, so they were kind of allowing that, but I'm not sure whether it is the same case in different labs too. So it depends upon the place you're working in. Okay, so okay, this is interesting part coming to NV Center and Diamonds. So NV Center and Diamond, there is a very small number of companies that are actually exploring this technology, and so which makes the job limited for this particular domain, and some of them do not have any vacant positions. When I was observing career pages, I did a lot of research to take uh, career for this kind of NV-centered environments, but I was unable to get it because there were no job vacancies available when I was researching on this platform. So most of the research is actually restricted to the academic institutions only. However, by analyzing the available roles, what myself and my cohorts have found that industrial skills required to really succeed in NV central environment are similar to those of the semiconductor pin qubits, with additional skills such as confocal microscopy and laser spectroscopy. Those kind of particular uh, key skills which they require uh, by the academicians. So what actually happened in academics is academicians have their own startup and they hire the team from outside. So it's mostly happening secretly, maybe for the government or for some other confidential things, which I didn't see NG Central Diamonds coming out in news so much. Though there are some here and there, some news are there, but I don't really see a breakthrough in Envy Center. But there are certain teams in different parts of country are working in Envy Center and Diamonds. Okay. So let's come to the trap ion skills. So trap ions is something I'll be discussing a bit more briefly in the upcoming slides. So if you see in the trapped ions, atomic molecular and optical physics is one of the most important subjects, since trapped ions means you're using an ion and you're suspending an ion and you're trapping an ion with electromagnetic field, and then you're using the microwaves. I think to control those ion to make this trapped ion qubits. If I'm not wrong, I have not dedicatedly worked in this domain, but I understand how things are being done. Okay, so one of the major skill is atomic, molecular, and optical physics. Those foundations are kind of very, very important. And this is certain, these kind of words, AMO physics is actually mentioned in an industry page, career pages. I've seen many career pages, they mention these words, atomic, molecular, and optical physics, hands-on trapped ion experiments. So they are, industry people are kind of very much keen and specific on what they're looking for. So, what are the words they used in the career page? I use the same thing in my paper also. So, so that's the reason why I say you can always go and read the paper. It's open access, so you don't have to pay money. Or if you're not a part of academic institution, also you can. It's open access. You can go and have a read at it. Okay. So yeah. So if you want to build a trap ion qubit, it actually starts with a vacuum chamber. Why vacuum chamber? Because vacuum chamber, uh, you can actually suspend an ion. You have to actually isolate a qubit. For that, you should not have any kind of stray gases. So that's the reason why they use vacuum chambers, where ions are usually calcium, yttrium, or barium. They are confined using the electromagnetic fields from microfabricated ion traps. So these ions are then laser cooled to near absolute zero, and their internal electronic states serve as the qubits 0 and 1. So here the lasers and the microwaves manipulate and entangle the ions, because you don't work with only one particular qubit. If you want to scale a particular hardware architecture, you need to work with multiple qubits. So those qubits must be, there is a famous thing which I wanted to share. The qubits must be isolated enough, but also should be connected enough. So isolated enough to not mix with, to not react with the external noise, but also the qubits should be connected within themselves to have the connectivity. If you don't have connectivity, then what is the use of having a qubit? The qubits must be able to have connectivity to have the operations in the quantum mechanical nature. Okay, so that's the famous quote I want to share. Yeah, so the lasers, microwaves actually manipulate and entangle the ions, while optical systems detect their states through fluorescence. So, in essence, if you want to build a trapped ion qubit, you need to master the precision optics, laser control, and quantum state detection at the atomic scale. Um, I think this makes a lot of sense from what I mentioned in the previous slide. And yeah, nearly half of the skills are, if you see in this slide, I've mentioned briefly about what is required. I gave proper justification for this slide. So yeah, nearly half of the skills fall under AMO physics. That's the art of this technology. But the rest you should develop, like time control, signal processing, hands-on experiment experience, data acquisition. Those are important post skills. Apart from the experimental, apart from working in nanofabrication, you should know how to analyze the data. So that's also one important point here. Okay. Yeah, foundational knowledge. AMO physics, laser cooling, trapping mechanism, we have already seen in the previous slides. And coming to the experimental skills, again, laser alignment is needed, and RF, radio frequency and microwave engineering for trap control, vacuum system operation, optical table alignment, because you need to, since I think trapped ions, though it is matured somewhat, but still you need to um, make it a bit more. There is a lot of fabrication uh, improvement should be done to, if you want to scale the trapped ions. Okay, so those kind of research are actually going on, and those are industry level research also, academic level research also. Okay, and the third point is again system software integration skills. So you can actually observe the pattern here. So in the previous hardware architectures, superconducting qubits and semiconductor qubits, I had the similar kind of structure, foundational knowledge, experimental skills, and the software integration skills. To be very honest, the pattern is kind of same only. You need, like for example, you need to know about particular areas of physics. Superconducting qubits needs knowledge in condensed matter physics. Tap ion needs knowledge in atomic molecular optical physics. Okay, and yeah, microwave engineering is very important. You need to know the foundations of any. If you take any hardware, you need to know some foundations of the microwave engineering also. And yeah, another common pattern which you observe in all the modality is having doing the electromagnetic simulation in tools like console is important, but sonnet is important, and HFSS also we discussed about in the superconducting qubits. Those are also important. They specifically mention those words. Having hands-on experience in these tools are mandatory. They have this in the career page, actually. Okay. Yeah, I think pretty much the pattern is same. You can see everything in the slide here. Now, coming to the qualifications, what kind of qualifications are important? Again, the physics. Again, coming back, it's physics because hardware is based on physics, right? You're creating a product from physics. So you need to have physics knowledge in that. Electrical engineering, applied physics, physical chemistry, material science. Again, the name doesn't matter. You need to have relevant skills. Okay, so what are the degrees for the Sabdayan? Mostly, they of course they require a PhD, and if you have relevant job experience, even if you have masters, that is also good. I have seen on one of the company's career page. I don't know which company it is, but they were asking for bachelor's, but bachelor's plus 10 years of experience. Then I realized what kind of skill they are. What kind of position they are hiring for. I researched on that and I saw they're hiring for senior technician roles. Oh, okay, so what the main reason why I'm saying this because many people can ask why I'm saying only PhD and masters, why can't bachelor's? Of course, bachelor students also have um, opportunities, but you need to have nearly a decade of experience. You know that too, you can go and become the lab technician roles. You can have the lab technician roles actually if you did bachelor's. I have seen that in one or two career pages. Big, sorry, big companies who are having a lot of money, who are having their own lab, they need lab technicians. So for lab technicians, you need to have a very good amount of knowledge, you know. So why they hire bachelors plus a lot of nearly decade of experience. One of my known person when I was working in IMDCNM, one of my friend has done bachelors, and she's working there for nearly 10 years as I think as a senior lab technician. So that is also possible. Again, it depends upon the lab whether they really want to have a bachelor student. But you should check up with the labs, you know. Okay, now coming to the neutral atoms. The neutral atoms and shutdowns are a little bit similar, you can say, because they all come and fall under the aim of physics category. So yeah, even in this required skills, aim of physics is very important, and scientific programming and data analysis those are also important, and laser systems again, as I mentioned, tabions and neutral atoms both are having a same kind of skills category. So if you know how to, if you have relevant skill in neutral atoms or tabions, the skills are actually transferable in nature. Okay, so yeah, we can see measurement of RF signals and hands-on experience with different quantum computing platforms, and then proficiency in Git and GitHub. Those are there, and also optical test equipment. Those are also one of these skills mentioned. And sorry, and what are the qualifications here? Again, physics is there. Physics is important. Um, okay, so coming back to the degree, nearly so as I mentioned, for most of the for all of the qubit architectures, PhD is actually very important, 100%. So as far as I saw, the companies which are working in neutral atoms, they require PhDs. Okay. Now, yeah, coming to important domain photonics. So photonics, many companies are actually working in photonics because the main reason is the application, the real application which you can use it in quantum sensing. So if you are aware about good in photonics, those knowledge can be used in developing quantum sensing products, which we will be seeing it in the upcoming slides. So many companies are actually focusing on photonics also. Okay, let's understand what is the difference between classical photonics and quantum photonics. So classical photonics actually heavily focus on wave aspect of light. For example, lasers, LEDs, which we have seen, which we have used, those have the wave mostly focus on the wave aspect of light. But in quantum photonics, they focus on the particle nature of light. So you might be working with one photon or entangled photons at a time, but the wave nature still exists. It's like you already know wave particle duality, right? So in photonics, mostly the wave nature of light is given um, much focus. So that's the major difference between classical photonics and quantum photonics. Okay, so it's not just particle only; it's the superposition of both, and that's the important part of quantum computing. The states are in superposition. The same thing is for the light also, wave and nature duality. Okay, so this is the difference between classical photonics and quantum photonics. For example, single photon sources. Actually, single photon sources are very important application which you will be using, if I'm not wrong, in quantum sensing. So that's the reason why I mentioned photonics is an important domain. You have a ready-to-make applications which can be used in defense and network and communications. You know, Okay, so what is the meaning of quantum integrated photonics? In the important skills which I have analyzed, one of the important skill which all the company requires is quantum integrated photonics, and I'm going to give a brief explanation what is the meaning of quantum integrated photonics. Your integrated means you are having multiple optical components like waveguides, beam splitters, phase shifters, modulators, and detectors that are fabricated and connected on a single chip. You can see this diagram here. It's just a simple diagram where all the components are in a single chip, and that's what integrated photonics is all about. So instead of having also when I was in Spain, I went to one of the institute in Madrid, and they were having all the equipment in on the table. So I realized yesterday when I was making this slide that this is that quantum integrated photonic chip can be a very good game changer because it's good for scalability. So if you wanted to do PhD, you can think about in photonics especially. You have to you can have a focus on working in quantum integrated photonics. Why? Because you have all the components in a single chip. So what does it mean? If you have everything in a single chip, it means you can scale it. If you can scale it, you can make a product out of it. If you can make a product out of it, you can have a money out of it, right? So that's the whole point here. Okay. So, okay, what does quantum integrated photonics do? It generates, manipulates, and detects quantum states of light. So that's the important reason why people are focusing more on quantum integrated photonics chips. Okay. Yeah. Now coming to the point of hardware manufacture of photonics. Hardware of photonics is slightly different from other architectures. So photonics actually mostly don't require the cryogenic setup. So so that means so what does it mean? It doesn't need cryogenics. It means photonic qubit can work at room temperature. If you need cryogenic means you need to have a separate dilution refrigerator. I think for that photonic qubits mostly don't need a cryogenics. Whereas some areas you might need dilution refrigerator for photonics, but not in most of the cases. Okay. Yeah, the third point justifies it. Some photonic components do require cooling. For example, superconducting single photon detectors, quantum dot photon sources. Those are subsystems and not the qubit carrier themselves. Okay, and since there is no cryogenics, there is very less loss of information. Thus, photonic qubits are mostly stable. Since if you keep a qubit in a cryogenic means you need to isolate the qubit. If you can't isolate the qubit properly, it will react to the environment. If it what happens when it reacts to the environment, it kind of loses the information, and that's where you need quantum error correction. Since you don't need a cryogenic setup in photonics, you don't. There is no loss. There is very less loss of information, and it's the so what does it mean? The photonic qubits are stable. You have to understand like this. And the major reason why photonics is important because you have a ready application in quantum communication. So in quantum communications, um, uh, quantum communication is used in cryptography. Okay, so if you wanted to have, you can also they also use in cryptography also. I was researching some jobs, and one of the bank actually require quantum cryptographic role. In that I have seen they use this kind of photonics qubits. I remember that now. So why photonic qubits are used? Because you can transfer it in a in a wire, optical fiber. If I'm not wrong, since I have not worked in that much, but I am kind of been in touch with all the news at present, so I can say you this. Okay, so there are ready-made applications in quantum sensing and QKD, and then satellite-based in quantum networks. So photonics are mostly used there. Okay, so now coming to the qualifications, you need to have again qualification. You need to know about AMO applied quantum physics and electrical or electronics or optical engineering. And what are the degree? Again, PhD degree wins and bachelor's and master degree follows the PhD. Okay. Okay, so we have completed all the hardware architectures. What are the skills needed? Whether we need PhD or not, and we have discussed in brief what are the key skills industries are requiring. Now we can quickly see what is error correction and how can we develop skills in error correction. Yeah, in order to build a fault-tolerant quantum computer, there must be a stable and non-state quantum computer. In order to build that, error-corrected quantum computer is required. Okay, so that's the introduction of why we need quantum error correction. And nowadays, in LinkedIn as well as in different platforms, I'm seeing there are a lot of job offerings for quantum error correction because you have a demand to to make a fault-tolerant quantum computer. And if you take quantum error correction, I can divide safely into two halves. One is theoretical quantum error correction, and another one is experimental quantum error correction. So let's see what do we need in theoretical quantum error correction. In theoretical quantum error correction, you are actually a mathematician. You have to develop the error correction codes from scratch. You need to do a proper research. You need to develop fault tolerant code. So that comes under a theoretical error correction. And what comes under experimental quantum error correction? You are going to apply those codes for in the hardware. You are going to take a particular hardware which gives a lot of noise, and you're going to apply those codes in depending upon the type of hardware architecture, you're going to apply those codes with the help of FPGAs and decoders. Okay, so those comes under experimental quantum error correction, and there is a opportunity for both theoretical error correction scientists as well as experimental error correction scientists also. Okay, so yeah, I have mentioned about what comes in a theoretical error correction, and yeah, what comes in a quantum experimental quantum error correction. Okay, yeah, you need to know about the FPGA program if you wanted to go into the experimental side. So actually, experimental quantum error correction, as far as I saw and observed and spoke to many people who are in experimental quantum error correction domain, I observed that you need to know about the classical side of uh, uh, correcting the errors. For example, you need to know about the FPGA technique, and you need to know the classical, control electronics. You should know, and you should know how to apply that error correction codes in a particular quantum hardware. So mostly people who are mostly industry IOs, experimental error correction people who have knowledge in FPGA control electronics. So those are very important domains, because you need to use those skills to correct the particular hardware, and these are important. Okay, and I've given you what are the domains and what you actually do and why it is actually critical. I will maybe I can you can take a screenshot of this slide. You can use it for your personal reference too. Okay, fine. I think I can move ahead to the next point. Next is quantum error correction skills. Of course, I already mentioned what are the domains are there. Theoretical error correction, quantum experimental quantum error correction is also there, and what are the key skills, hardware skills required. So the hardware skills required are expertise in FPGA platform and expertise in implementing the QEZ hardware, decoders and hardware, and yeah, those are the important points which people are looking for. And yeah, and these are the skills, software skills in quantum error correction. For example, again, you need to know about the high performance decoders. You need to know some skills like Python, C++, not in depth, but at least you should know how to rectify the errors, you know. And you need to know about the theoretical aspects of error correction. How do they even mathematically derive, I mean, mathematically create a new codes. Okay, so those are important. And then yeah, expertise in implementing the fault tolerant quantum computing. Those are important. And scientific research, publication, and error correction. Because how do industry knows that you are an expert in this field? So that's the point here. Okay, so what are the degrees required in error correction? Mostly PhDs are required. But here is the catch. I have seen a lot of companies who are hiring experimental error correction people. There they have mentioned master's degree, but they require a very good amount of experience in FPGAs. So if you have master's degree and also you have very good knowledge in FPGA and have implemented and done some research in this quantum error correction, I think master's degree is good to go for experimental side of error correction. But for theoretical side of error correction, according to my observation, one needs PhD. I have done this observation for a couple of months and I got to know this. Okay. Next is what are the qualifications required? What are the key names which company is mentioning? So, for example, computer science, they are mentioning computer science background, physics background, math background, quantum science and technology background. They mention these words in the career pages, you know. And yeah, they one of the career page also mentioned want a specific people who have done PhD in quantum error correction. PhD in quantum error correction means you are developing a theoretical side of error correction. You worked in theoretical side of quantum error correction. You worked in pure abstract math. So those are called as PhD in quantum error correction, you know. Yeah. So those are the qualifications in quantum error correction. Now coming to the sensing, quantum sensing part. So what actually is quantum sensor? Quantum sensor uses the principle of quantum physics to measure signal with extreme precision. And quantum sensors are designed in such a way that it detects even the tiniest changes beyond the reach of classical sensors. So that's where quantum sensors majorly work in. You know, you can use the quantum mechanical principle and can detect the tiniest changes beyond which classical sensors cannot detect. So that's the reason why they use quantum sensors. Okay. And what are the major types of quantum sensors? You have atomic clocks, quantum magnetometers, quantum gravimeters, quantum imaging, interferometers, quantum inertial sensors. So those are the major types of quantum sensors. And I can say quantum sensor is a vast domain. And if you want to work in a specific application, you should really check which lab or which company is actually working in what particular application. You know, so those are important. Mostly, what I observe in quantum sensing is they require key expertise since again it's a product. So wherever the product is involved, there you need to have there the industry requires PhD. Okay, so you can think like that. Wherever you make money, wherever there is a product involved, especially quantum is a niche domain. their industry requires a PhD or at least master's plus 5 years of experience, which comes up to having a PhD. Usually, PhD is 4 years of experience, but if you have if that industry doesn't need a PhD, but they need at least 3 to 7 years of experience, which comes up to having a PhD degree. So you need to have good amount of experience to get hired in the industry also, because these are very niche domains and a lot of quantum subtle skills are required in this. Okay, and what are the applications in this? Navigation in aerospace, earth and environmental monitoring, and defense and security. Mostly people are working for the defense. So uh, people are more confidential in what kind of project they're doing, and we don't get more information outside. Yeah. What are the skills required? I have also already mentioned cold atoms, laser system design, testing, quantum optics. Why quantum optics and all these optical related stuff required? Because uh, photonics is important. That's the reason why I mentioned photonics, where since photonics doesn't need cryogenic and it can and the qubits are stable without any isolation, and that's the reason why they use this in quantum sensing. And photonics is kind of integrated domain with the quantum sensing. So if you have worked in photonics, you can work in this kind of quantum sensing applications. Yeah, as I mentioned, you need to have a PhD or master's plus good amount of experience, 5 6 years of experience. Yeah. What are the qualifications required? Either physics, applied physics, engineering, data science, or geophysics. Those are the industry relevant, specified words. You know. Yeah, I think we have come to the end of our session, and we have discussed about different types of quantum hardware, what are the skills required, and we have seen about error correction. We have discussed in brief what are the industry's job skills required for theoretical error correction, quantum error correction, and we have discussed in brief about quantum sensors also. And yeah, there are different domains like quantum cryptography, which I have not covered here, but it's there in my paper. You can have a look at it whenever you are free. I have also mentioned about quantum machine learning, also quantum finance, also, which I have not covered here. Okay, so I think I'll stop sharing my screen. Uh,
Thank you, Dr. Shalini, for your
Thank you so much.
presentation. Uh,
I hope
the,
the session was insightful. If there is any questions, please let me know.
yes, we have some question. One of the public, Mr. Baskaraya. Dear ma'am, I have AM Tech applied optics and have experience with laser system LiDAR. 1 year, optical tweezers, 1 year, and have a PhD in nanomaterials for optoelectronics application. Please let me
Mhm.
know any job option in photonic quantum industries.
Hello, Bhaskar. I think you are from India, if I'm not wrong. If you're working in India, there are a lot of, I can say from Indian perspective, uh, there are a lot of academic institutions in India which are actually working in quantum sensors. For example, IIT Bombay is requiring a lot of, they wanted to hire people who have experience in these kind of domains. So I think you can get in touch with one of the professors from IIT Bombay who are working in the this kind of quantum sensing domains. If you have done photonic quantum, have experience in this.
Uh,
Awesome. So, okay.
okay. Have another question. What is used quantum computing in theoretical physics? Kumar.
What is use quantum? What is use quantum? I mean, I couldn't understand the question. Nitish, can you
Yes.
please? What is use quantum computing and means? What is the meaning? What is use quantum computing and theoretical physics?
I think Kumar refers the applications in theoretical physics investigation research.
Okay, I can say one thing. Theoretical physics. Actually, experimental are the one where you apply the the actually theoretical physics is something you are working with the pure math and physics, and experimental people are the one who convert that theoretical theory into a product. Okay, so application means there are different domains, right, in quantum. So what kind of application are you specifying to?
Okay. Uh,
um,
yeah,
I want to the question is not very clear, so I just explain it in a very general way.
it's okay. Have another question. Why is MB Diamond interesting? What are advantage MB
Okay,
than
what
Hune?
why is MB diamond interesting? um NB Center and Diamonds. I think NB Center and Diamond also has some applications in quantum sensing, if I'm not wrong. And yeah, if you're asking for the advantages, I am not very sure about the advantages of NV Center and Diamonds, since I have not went into deep of NV Center and Diamonds. So I'm sorry, like I'm unable to give a proper full answer for this.
Okay,
Applications of applications of quantum computing and
it's the
theoretical
same
physics.
question.
Like Nitish, I already mentioned, like what is the application of quantum computing? No, theoretical physics only has. I mean, uh, the question, I should reverse the question. Actually, theoretical physics is the one where it is applied when an experimental person takes the theoretical physics and makes. I mean, make take the physics equations and create a product out of it, and that's the application. So your question should be, how come theoretical physics is helpful in application based of quantum computing?
We can hear you, Shalini.
Okay.
Yes, we can hear you.
Okay, so
Have another two questions. One
okay.
of us is the Latin America ecosystem often relies on community-driven initiatives rather than institutional funding. How do you see the role of student chapters, meetups, and hackathons in preparing the regional quantum workforce?
I would always suggest people who takes my advice. I always suggest and advise people to do self study. Though there are workshop and hackathons present all over, there are a lot of quantum computing workshops happening. But you have to take a lot of input and lesson from those workshops. But what is gonna help you and what is gonna help you develop those skills is only self study. When you're doing university, if you're in university, you have to be very observant in the internship which you want to do. If you're not studying in university, if you're a professional, you need to do a lot of self study apart from your working in other, I mean, apart from your work. So that's how you can develop a real skill. Real skill takes a lot of time to develop, and if you want to be an expert, you have to be in a particular field for more than 5, 8 years. That's where you become a real expert actually. And coming back to your question, hackathons can help, but self study is important. You should not rely only on hackathons and webinars or other stuff. Okay, you can use it for education purposes, but self study only will help you.
Uh, Thank you. Have another question. How can
Okay.
professional for traditional files, classical engineering, make the transition to the quantum file?
Okay, so how come people who don't have experience in quantum, I mean physics especially, wanted to come into quantum domain who are working in other fields? Is that the question?
It's the question. How can a traditional engineer make the transition to quantum technologies involved in this new area?
Okay, I can say you one important point. Whoever asks this question, always ask yourself what kind of, since I mentioned the different domains here, you can ask question to yourself. I'm not sure what kind of domain you're actually working in. If you're working in, I assume that you're having some kind of software knowledge, have some Python background, and have some experience in coding and all. So if you're a software person or working in IT and know some ML techniques, I would suggest you to go to the ML side. Or if you're an engineer who are creating a product, I would suggest you go to the hardware side because wherever you have your tenure undergraduate in, you try to make your skills in quantum closer to that. If you are having experience in ML, because this world is, everyone is learning ML nowadays. So if you have skills in ML, I would suggest to stick with QML. If you are having developing a product in a company, or you're in working in a lab, you're in a Silicon Valley, I would suggest you can go to the quantum hardware. Or if you want to stay in quantum in the software side, but you don't want to do QML, there are a lot of options like applications like quantum cryptography, quantum finance is there. You can go to those directions. But mind it, there is no jobs actually at present where people are actually hiring for quantum finance. There is a company called HSBC who are hiring having knowledge in finance background, but of course they need research paper experience. They need to have track record experience. I mean the real quantum skills, So you have to check with the career pages of HSBC too. They hire people who have quantum finance background.
Thank you, Ms. Shalini.
Okay.
Another question about uh, Baskaraya. Dear Sir, I wish to know quantum photonics jobs at abroad
Mm-hmm.
outside of India.
Okay. Photonics. There are a lot of universities which are working. So there are companies like Quantium is working in Fab Division, and I think New Quantum is working in photonics. I'm not very sure. Um, Apart from Quantium, I'm unable to think. But yeah, there are a very good amount of photonics companies. I mean, startups who are working in photonics. But I'm unable to get the names of it. Maybe you can just type in Google. You will get what are the list of photonics companies. I'm sorry, I'm unable to get the companies in my mind apart from Quantium. I think this can answer you well.
Thank you. And only finally question.
Okay.
If you were to design a roadmap for Latin Americans' quantum education, what
Mhm.
key milestones in training, research, and collaborations would you include to help the region catch up with global trends?
Okay, so what kind of roadmap, what are the milestones which I will create to have the workforce development in quantum? Is it true? Is that the question?
Yes, it's the
Okay,
question.
so first important point, if I am uh, making this milestone is, first I will go um, first point is I would always see what kind of employment opportunities available. So I would always suggest people to go and look out the career sections of different companies if they want to work in industry. And that's the first point, to have knowledge of companies which they are working in. Because always remember that we need to know the business aspects of quantum companies. If they have business, you can they if they have business, it means that they will hire you. If they can hire you, then they can pay you well. So always think in the business perspective. So that's the first milestone I would suggest. And second, in the reading perspective, if I wanted to keep a milestone, I would suggest people to have exposure in quantum domain for 6 months to have exposure in different domains. For example, there are QML domain is there, quantum finance is there, QNLP is there, and quantum hardware is there, cryptography is there. I would suggest people to understand the foundations of these domains and what interests you more. You should take that and work on that particular field and focus on the research area because quantum at present is a lot of research. So I would do that.
Thank you, Dr. Shalini. Uh, we greatly appreciate the time you have given us today and how much you have contributed with your knowledge. Thank you very much, and we
Thank
hope to have you back here in the future.
Thank
Thank
you so much. Thank you all. Bye. I'm leaving now. Thank you.
Bye. Thank you, Dr. Shalini. We will now take a 1 hour break. We will see you back at 11 a.m. Chicago time to hear from Dr. Mariana Filipova. Please stay tuned and thank you very much.